Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, hello, everyone. I'd like to introduce Doug Turnbull. Doug Turnbull's a sixth-year grad student graduating from UCSD, and he's worked with both Gert Lancrete and Lawrence Saul. He does machine learning research and music, sort of computational audition research. So he'll tell us about what he's been doing. Thanks.
Thanks for having me. So I'm going to talk about really two things today, both a content-based music search engine that I built and a new direction that involves human computation to collect data about music. And so it'll be pretty informal talk, so please ask questions or stop me if there's anything that's unclear. So so I'm from the Computer Audition Lab at UC San Diego. It's a new lab, but we have a great new group of professors that are really supportive of this sort of research. So hopefully you'll see good things in the future. So I'm going to make the case here that this is a fascinating time for music, specifically digital music on the internet. I call it the great proliferation of music. There's tons of consumers. I guess I should have put in the number of Zunes sold, but there's been 110 million iPods sold, and they are huge. They can hold thousands and thousands of songs. So people are listening to music everywhere. If you've ever hung out with high school kids, you know that they get the newest MP3 player as soon as it comes out. So there's also these internet radio companies. Pandora is probably the most well-known in the United States, and they have 7 million users, and a lot of them come back every day and use it while they're working. So there's a lot of people listening to internet radio. There's also tons of users of social networks, and social networks are now having music tied in with them. So it's a very social music experience. There's also a lot of people producing music. AMG All Music is probably the largest commercial database of music, and they have 11 million songs. There's another internet radio company that was just bought by CBS called Lastfm, and they have individual deals with 20,000 record labels. And the least thing you're probably aware of, but the most important thing to me is that there is a company called Audacity that makes a freeware music editing package, and it's downloaded 1 million times a month. So basically, the point here is that anybody with a laptop computer, this free software, and a microphone can be their own, recording studio. They can take those songs, post them on MySpace, and they can be their own, record producer. And if you think about all the bands playing in all the venues in all the world, recording their songs every night, there's just a staggering amount of music that could be on the internet in the very near future. So my research is involved on connecting both the consumers and the producers of music. So if you think about music on the internet right now, there's really only one way to find music in a commercial setting, and that's query by metadata. So you go in, you know the name of the artist or the album, and you go to that site and you just buy the album on iTunes or some other company, or like the new Amazon service. But you have to know exactly what you want, so this is fairly limiting. There's been a lot of fascinating and fun research systems that are like query by humming systems, where you hum part of the song and they return, songs that match. There's also fun beatboxing ones that are fun. But the problem is not that these systems don't work well. The problem is the users don't work well. And so people tend to not have the sort of talent to be able to specify music that they need or want. So although this is a fascinating research direction, it's unclear that these will really be commercially viable. The hot new direction, which is something people here at Microsoft Research have been working on, is this query by song similarity. You can take a lot of different approaches. You can do collaborative filtering. Yahoo's really big into that right now. There's acoustic similarity, which is something I'm really interested in. But the problem with these song similarities paradigm is that it's hard to specify exactly what you want. So you take a song, and what about that song is what you want in the sort of other songs you're hoping to retrieve. So the approach I'm going to take is sort of a query by song semantic description. And if you've used Microsoft Live Search and you want web pages that it's a pretty standard paradigm that everyone knows and is familiar with. It's a hot topic in computer vision where people want to find images with polar bears in them, so they do some sort of content-based analysis of a large library of images, and they get back images with polar bears in them. And so can this work for music? So just to sort of specify the problem a little, here's a song by Frank Sinatra.
Fly me to the moon, let me play among the stars.
So maybe you're familiar with the song, but even if you're not, there's a lot of semantic information that you can derive from that signal. So we can start with this audio signal that we just heard, and we can put words like jazz, male vocal, sad, mellow, slow tempo, and that's how we would sort of annotate that song. And then once we have an annotation of the song, we can turn it around and we can rank order songs in a large database, and we can give those songs to people. And that's the retrieval problem. So the approach we're going to take in our model, in our system, is to have a probabilistic model that models the relation, or the joint probability of sort of the audio features that we can extract from music, and these sort of semantic descriptors, or these tags or words. I'm going to actually use the word word to describe these things, but the new buzzword is tags. So you can, I'll use words, but it means the same thing. So this is how the system works. It's a standard sort of supervised, multi-class, multi-label sort of problem. We start with training data. We have songs and an annotation of the song, of each song. We're going to represent the semantic data as a vector over a sort of vocabulary of words. And we're going to extract audio features from the songs. Then we're going to assume some sort of parametric model and estimate the parameters of that model. And then we're going to take a novel song, extract features, and then annotate that song and output a music review. Or we can take a text query and use that text query to rank order all the songs in our database. So I'm going to break this down and into each box. So that's just sort of the overview slide. All right. So, and then the last and most important step of any scientific endeavor is how well did we do? And this actually turns out to be one of the most difficult problems here, because music is a very subjective thing. Yeah, you know, lyrics is something we haven't explicitly looked at by design because it's its own animal. It's really a text-based problem. It's text mining. And we do actually do a lot of text mining, which I'll talk about in a little bit for sort of semantic information, but lyrics are certainly a very useful thing, and just something we haven't spent time working on. So the training data is the beginning of the system, and this turns out to be the most important and most time-consuming part of the process. We've looked at three ways of getting semantic information about music. The first is a text mining project that we collected song reviews, and we did some processing of those text documents. We extracted a vocabulary of 317 what we call musically relevant words, just that were picked by hand. And so this might be a review from AMG AllMusic for Strawberry Fields Forever by the Beatles. And if you just do the simple bag of words thing, there's a number of really useful words like lethargic, peaceful, a folky ballad. So there are some good words that you can identify from the text document. It turns out if you show these words to, if you just take these bag words, shuffle them around, and just show the list of words, they tend to be a pretty bad annotation of a song, just qualitatively. We've done some testing with users. But there's deeper problems, which are, you know, there's a lot of banter, opinionated rants about various things. This says that, you know, Strawberry Fields Forever is not so much about a physical place, but about a state of mind. I mean, it's really hard to derive sort of semantic meaning from that sentence. There's other things which are even more detrimental, which in this part it says that there's a mellotron that's mistaken by some for flutes. So in this case, we would extract the word flutes, but actually there's no flutes. So we've extracted a token that's incorrect. And there's plenty of places where people say this song does not rock. And so now if we did some naive bag of word stuff, we would identify the word rock, and we'd have a label for a song that doesn't rock. So there's a lot of problems with this system. The good news is there's tons of data, and it's cheap to collect, but the bad news is it tends to be noisy, it can be opinionated. There's sort of a natural disconnect between someone writing a natural language document and someone who's trying to describe the word with tags, or the music with tags. The second thing we did, which is what a lot of people have done recently, is conduct a survey. And And Microsoft bought a company called Mongo Music a couple years back. They had a large database of this sort of data. Pandora is another example of a company that pays 50 musicians full-time salary and benefits to sit there and label music. And it's a very slow and laborious process. We just did a very quick research academic thing where we assumed some sort of vocabulary of words. We had genre words, emotion words, usage words, which are like while driving or at the beach. And we paid 55 undergraduates to sit in a lab and just label music. And it's, a lot of them enjoyed it actually, but, and we had to pay them, of course. We produced the Cal 500 data set, which is a freely available data set, where each of 500 songs by 500 unique artists have been annotated by 3 people or more, where I'm going to talk about this a lot more later. And this is the sort of paradigm. You're listening on headphones and you see, this is the instrumentation panel, and people can say whether there's a banjo, whether they don't know if it's a banjo, whether it's present, whether it's prominent, whether there's a banjo solo, that sort of thing. So you can imagine yourself in a basement for hours and hours doing this sort of thing. It would get pretty tedious. So the good news is you get very good data. It's tailored to the exact application, but it's expensive and laborious. And laborious is actually a very bad thing because people can tend to start getting lazy and clicking boxes that they don't necessarily intend. So there's some really fundamental social problems with this approach. So the last and most compelling direction is something that's an ongoing project. It's called the Human Computation game, or a game with a purpose. It's basically a web-based multiplayer game that people come to your site, they listen to music, and through the gameplay they give us tags. The ESP game, which is actually now the Google Image Labeler, was developed by Louis von Ahn, and he won a MacArthur Genius Award and is very famous now for coming up with this very simple idea. We produced a game called Listen Game that it's in its about 5th iteration now. It looks a little like this. So you basically, you have to make avatars to be part of Web 2.0. Has to have nice rounded corners and nice color scheme. And you can pick a genre, like in this case, maybe we'll pick the rock genre. And then you're listening to music, in this case with 5 other people. You're newbie at the top. And you're listening to maybe this Green Day song, and you think the song is energetic, so you rub the genie, and the genie appears. We have tons of these little sort of kitschy games in the middle. And then you see what the other people pick. So in this case, all the people picked energetic, so that's a very good label. And Charlie picked gritty, but since they were in the sort of minority, they don't get any points, and so on and so forth. And this is another example of a game where you're just trying to say male vocals, female vocals are instrumental, and in this case, everybody identified this being a male vocal song. And then you get scores, and you can imagine social networks, and we're actually plugging this into Facebook as we speak. So, and I'll be happy to show you this game if you want after the talk. But so again,
evaluation of how good the tagging is?
So yes, we wrote a paper at the Music Information Retrieval Conference this year where we basically compared the survey data to the game data. The problem is you have to, like I said, the problem is it's really hard to get people to play your game. And you have to make a very viral game, and that tends to be very difficult. Even Louis von Ahn has only been really successful with one game, and he's produced about 5. So it's hard to produce a game that is inherently boring because you're just labeling. And so the data you do get is usually very good, especially if you have lots of people playing and you get a distribution over the sort of words. And it is very useful. It's much more useful than sort of text mining data. So that's the data. So now we have a training set of songs and semantic annotations. We're going to assume some vocabulary, and we're going to represent our song as a vector over this vocabulary.
Sorry, your data was obtained from Reddit?
The data I'm going to describe is actually from our survey, because we collected the most of it. In the future, the goal is, and that's only for 500 songs, the future would be a successful game, which again is hard to do, and we would have thousands of songs annotated by thousands of people, and that would be just, in fact, Louis Van Ahn was able to do the best sort of content-based image search engine without actually ever doing anything content-based by having so many people play his game. He could sort of skip all computer vision, and that's where the real power comes from. So, but again, you have to have the users playing the game to make it useful. So right now we're going to just talk about survey data that we paid undergraduates to give us. So we have this vocabulary of 174 words. We're going to basically represent the data, and then we're going to extract some audio features. So what does that look like? So we have instrument words, genre words, emotions, rhythm, energy, all sorts of semantic tags you could associate with music. And we're going to create a vector, a semantic annotation vector, which each element of that vector is a weight where it's a relationship between the word and the song. So if we have that Fly Me to the Moon song we played earlier, and we have a 6-word vocabulary, funk, jazz, guitar, female vocals, sad and passionate, and we ask 4 undergraduates to tell us, does this song have funk in it? Nobody thinks that Frank Sinatra's funky. And then if we say, how many say it's jazz? 3 out of 4 say jazz. 4 out of 4 identify it as guitar. Everybody says there's no female vocals, and this is sort of your real valued vector over this vocabulary. So now imagine 174-word vocabulary, and that's the sort of semantic representation. So the audio representation, we're basically going to take a bag of feature vector approach. We're going to pass a short time window over this audio signal, and we're going to extract a feature vector for each hop of this window. And so we get a time series of feature vectors, and then we're going to assume it's a bag, so we're going to ignore all temporal information. The features we use are the sort of standard speech recognition features called MFCCs, mel frequency capture coefficients. We append the sort of temporal derivatives, so we have some short-term temporal information. And I'm not going to say too much about this, but we have about 5,200 39-dimensional per minute of audio content. So for a 4-minute song, we might have about 20,000 feature vectors.
So how polyphonic are the bilingual songs?
They're mostly Western popular music in the sort of rock, blues, pop, alternative tradition.
So they're pretty polyphonic.
Yeah.
Fundamentally underneath it, MFCC is built on assuming it's a single resident producer.
Right, an individual. Well, you know, MFCCs, pretty much everyone in the music processing information retrieval community uses MFCCs at a fundamental.
That doesn't make it right.
It doesn't make it right. But there have been a lot of studies, and we actually, we've tried modulation spectra features, we've tried other standards, low-level spectral features. We've tried chromograms, which are sort of a basically you fold the spectrum onto musical notes. And there's lots of things you could try, and we've thrown a lot of different variants at it. But and MFCCs plus delta tend to work better than anything else. So, and that's pretty consistent with the literature, I'd say. You're right. But a lot of people really spend. I'm trying to sort of take the machine learning approach as opposed to the DSP approach to this problem. So we'd like to just use low-level generic features and then see how well we can model them. So that's the representation of our data. The model is sort of the core piece here. We use the supervised multi-class labeling model. It's very simple. In fact, it's a reaction against more complicated models. It's just one Gaussian mixture model for each word in our vocabulary. And the key idea is that we're going to train that Gaussian mixture model based on the songs that have been positively associated with that word. So if we have a romantic, if romantic is the word we're trying to model, we have a set of songs that people have said these are romantic songs. We're going to just use all the features from those songs to train our Gaussian mixture model. And again, the Gaussian mixture model is over our feature vector space, which is this 39-dimensional mel frequency capsule coefficient feature vector. And this model was originally proposed by Carnero and Vasconcelos for the task of image labeling. And the benefit is it's very scalable and very parallelizable. So they've done this on images at Google for hundreds of thousands of images, and it tends to work very well. We modified it to handle real valued weights. They sort of had binary labels. We have real valued weights since music is very subjective in nature. And we have shown how to use it for multi-word queries, which I'll talk about in a little bit. So Gaussian mixture model is just a convex combination of Gaussians. And the parameters of this model are the mixing weights for each Gaussian and the mean and the covariance for each Gaussian. We use diagonal covariances. So we only have, you know, about, well, depending on we only have R times 39 means, 39 covariances, and then if we have R mixing weights, we don't actually have all that many parameters for each word in our vocabulary. And we're going to just use the standard EM algorithm to estimate the parameters of these Gaussian mixture models. So that, yeah? So the features are 39 dimensions. Yeah, sorry. Please stop. I'm sort of rambling through that, so definitely stop. So again, we have our song. We have our window that we pass over the features. We take our 39-dimensional features and embed them into some feature space, and then we're going to model them with Gaussian balls or hyperspheres here. And so the sort of standard way you would estimate the features is you'd start with all your romantic songs. You take a union of, or you sort of take a union of all the features. So this is my romantic word. These are my 6 romantic songs. I've extracted these feature vectors from each song, and I'm just going to take the sort of union of all of those bags of feature vectors, and then I'm just going to use the standard EM algorithm to estimate a Gaussian mixture model for each word in our vocabulary. It turns out that because we have hundreds of thousands of feature vectors for some words, and the EM algorithm is, converges to a local optima, the densities that we produce are decent, but we can certainly do better. So,
How many seconds
so an MFCC, and when you adapt MFCCs for music, you use about 25 millisecond windows, but we've appended derivatives. So we look at about plus and minus 3 time steps. So we have about 60 or 70 milliseconds worth of information in each.
So there's an interesting thing you might try, if they have time, which is to take a bunch of these vectors,
Mm-hmm.
commute them, and show them to people, and say,
Right.
75 milliseconds of music. Is that romantic?
Yeah. So it's hard to do that because you can't actually render 75.
No, but you could. I mean, you could play. We've done experiments like this where you play
Right.
75 milliseconds, and you can't even determine whether someone's male or female.
Yeah. Right. And so there's this sort of number floating around out there that's 250 milliseconds, and that's the amount of time it takes someone to make a lot of basic sort of, is this country, is this human speaking, is this a male? And it's sort of, that number, 250 milliseconds, is sort of the lower bound of being able to derive any sort of semantic meaning from sound. And so it's, what's that? Right, I'm asking a lot of the model. Again, there was sort of a reaction in the semantic image labeling where they went from trying to do things like segment images and try all these really hot, sort of medium level features. And the state of the art right now is to go back to these really low level sort of filter bank coefficients and try to model those and put a lot of the energy into the machine learning as opposed to the sort of intermediary level, because it just introduces so much noise. So you're right, we are asking a lot of the model, and that's sort of by design. And actually, this is really just an exploration of, can we model a lot from small, basic, short-term features? And the answer is the features sort of encode timbre, or an attempt to encode timbre, which is really important for us in the sort of recorded tradition that we're in. So I think you'll see. We'll see how it works when we get to the results. So the next thing you could try is called naive model averaging. Basically, now we take each song, we learn a Gaussian mixture model for each song, and then we just concatenate the set of, or we take the set of all of these Gaussian components and make this one Gaussian mixture model. This is sort of a non-parametric approach. So as the training set size grows, we get more and more Gaussian components. And this actually is a very good density estimate, but it becomes prohibitively expensive to evaluate. So the third approach that we use is called mixture hierarchies. We start like we're naive model averaging. We take our songs, we estimate a Gaussian mixture model for each song, and then we basically soft cluster Gaussian mixture components and produce a density estimate. So the intuition here is that 4 of these songs have a lot of density in this sort of where this pink region is. It's color-coded just for your own viewing pleasure, but there's not really color codes in Gaussian mixture models. But there's pink in these 4 romantic songs, so maybe that's an area where we'd expect to see density for romantic songs. But maybe there's this gray ellipse down here in this song, but no other song really has that, so we wouldn't really want to put a lot of energy into modeling the density in this part of the feature space. So, so it's sort of it's a regularization step, because we're basically representing each song as a distribution, which is sort of smoothing the feature space before we try to model the word distribution.
So do you ever discard? Do you have a junk model or anything like that?
Like a background model, or
especially the second model?
One of the things we have been looking at is tying parameters for all words and trying to learn what's the generic audio feature background model, and then trying to discriminatively push Gaussians for each word. But that's very much like a work in progress. So.
I can imagine like the gray thing is not, it might only be a subset of this, the frequency thing.
Right.
Romantic, and the rest of it's just sort of song.
Yeah, it's just noise, right? Yeah, I mean, definitely we can do more than this with some of the new distributive sort of GMM modeling techniques that would either tie parameters to get rid of background stuff and then just do. There's definitely a lot we can do with this, and it's very exciting, but this is sort of the first pass at it. So this is very computationally efficient, it's very parallelizable, and it turns out to produce better empirical density estimates when we go to evaluate the system performance. So, so that's our model. We have 1 Gaussian per word, and we use the EM algorithm to estimate the parameters of those Gaussian mixture models. So now we have a new song, and we want to generate an automatic music review. So we do what every good machine learning student does. We use Bayes' rule. We take our bag of feature vectors from the novel song. We make some assumptions about we just assume the word prior is uniform, just because we don't really want to model how popular words are. We want to actually have a good model for all words in our vocabulary. And then we're going to make the naive Bayes assumption that all feature vectors are independent given our word. And this produces a posterior of a word given the bag of feature vectors for our novel song. If we look at the set of these posterior probabilities, we have the parameters of what we call a semantic multinomial, which is, which I'll show you in a second what it looks like. And basically, we're just going to pick the peaks of the semantic multinomial. So if that didn't make any sense, here's a song by the Red Hot Chili Peppers. And this is the posterior of all of the 174 words, which are along the x-axis here, given the audio feature vectors. And if so the heights of these bars sum to 1, and they're all non-negative. So, and if we just look at the peaks of this semantic multinomial, we get words like angry, not calming, not tender, dance pop, male vocals, heavy beat, exercising, aggressive, rapping, and pop. This sort of gives you a flavor for the vocabs like. And if you think about that Red Hot Chili Peppers song, maybe it's kind of like a dance pop song. Maybe it's angry and not calming. So those are the sort of words that we can use to annotate this song. All of these are in test sets. So so we did tenfold cross-validation and stuff. Yeah.
Pick some threshold above which.
Yeah.
What happens if you lower that a bit?
Right.
Bars are pretty close.
Yeah. I mean, once you have this is actually pretty powerful, and I'll talk about how this is sort of a powerful representation. This is basically an index into your song over a vocabulary, and you can do lots of very interesting things once. I just picked the top 10 to show you that there's sort of, at least they're interesting words that are popping out of this system. And in fact, if we make use of the fact that we have certain genre words and we have certain emotion words, it's this hierarchical vocabulary, we can put the most likely words into this natural language template, and this is a Snoop Dogg song. This is my Southern California shout out.
One, two, three into the four. Snoop Doggy Dogg and Dr. Dre is at the door, ready to make an entrance, so back on up.
So, and we can output what we call a music Mad Lib. We have a template. We put in the most likely words, and we call this is a dance poppy hip-hop song that is arousing and exciting. Features a drum solo, backing vocals, male vocals, and a nice acoustic guitar solo. There's actually no acoustic guitar solo because it's a hip-hop song and there's not many solos in it, but it's a place in our template, so that's what it thinks is most likely to have a solo of.
Do you include negative words like boring?
Yes. In fact, in these, you see there's like the word not tender here, not calming. It's because we actually, for emotion words, we ask, is it calming or not calming? And they have a slider, and instead of, we just sort of think of it as two tokens rather than one token with a value.
Your 500 songs, did they come from 500 separate albums?
Unique artists, yeah.
Artists? No, I'm asking about album.
Well, yeah. Yeah, so 500 artists from 500 separate albums.
Oh.
We did get past what's called the artist filter or the album filter.
Well, and then the spectrum of music tends to be very dependent on what the producer is.
Right, definitely.
So you've prevented contamination.
Yeah, right. That's right. I can't say that there's 500 unique producers though without checking, but
But there's
can't.
500 albums.
Yeah. So, and here's another song, the song you heard earlier. I'll play it again.
Fly me to the moon, let me play among the stars.
So this is a very different song. It's a jazzy singer-songwriter song that's coming. So this is all 100% content-based, based on the audio signal. This is a test set. But of course, these are my cherry-picked examples, so we'll have to wait for the qualitative.
Terrific ones. If somebody sticks Spanish on the web and they can't say the reads, they're still going to write a nice mail about it solo.
Right, right. So this is really just showing off what the system can do. It's not really a user experience. We haven't got there yet. Although I'll show you a search engine at the end. It's more like what I would do to show off the system, not what I'd expect users to use. So now, so what we're really interested in is retrieval. We have these semantic multinomials. So we calculate the semantic multinomial to sort of index each song in our vocabulary, or sorry, in our database. And to do multi-word queries, we basically just construct a query multinomial, which is just, we take the string that the user types, and if they type 3 words that are in our vocabulary, the height of each of those words is 1/3, and it's 0 otherwise. And then we take the KL divergence between the query multinomial and each of the semantic multinomials in our data set of music. So what this looks like is, here's a 3-word query with pop, female lead vocals, and tender. And so this is the constructed query multinomial. You can see each height is about 1/3. And these are the top 3 songs that we would return based on the minimum KL divergence. And it's a Shakira song, Alicia Keys, and an Evanescence song. And these tend to be pretty good female pop vocal words. So here's some more qualitative responses. If I just do a 1-word query of tender, I get this song Guinevere by Crosby, Stills and Nash.
Guinevere had green eyes.
And here's a song from Jewel.
Wanted nothing more stranger from the east.
So these, and if you follow Art Tatum and John Lennon and Tom Waits, these are all pretty tender songs. I would say you have to be the judge, of course. If we do something a little more objective, like female vocals, we get Alicia Keys Falling, which is she was a Grammy Award winning artist. Shakira.
You're the one I know. So I learned to cook and
Did you do any kind of even anecdotal review to see like what harmonic features tended to come up and indicate tender, for example?
Right.
I mean, female vocals it seemed like I could guess, but tender, I'm just really curious. Is that really tender, or do those songs have an interesting similarity that isn't necessarily tender, but it's something that was...
Right. So unfortunately, the features, MFCCs, are sort of not very interpretable, which is a problem. And certainly, you could look at instrumentations that generally produce tender sort of sounds, like it's quieter, it's maybe uses flute or whatever. You could actually reason away why a song is a tender song or not, but again, we don't. The point is we're pretty agnostic as to this is just a tag. These are a bunch of songs associated with that tag. Let's see how the machine learning sort of does. And so we haven't really done this sort of, a lot of, I've given this talk to various music institutions, and that's what they're most interested in, but unfortunately, I don't have good answers for that. Was there another question? Yeah?
When you have something objective like female vocals,
Right. Yes or no? You're right or you're wrong.
what lets you rank one thing above another?
It's just the KL divergence between the semantic multinomial. So this is my.
Like if it has no other labels but female vocals.
So we're actually, so this is all content based. So we have the semantic multinomial for each song in our database, and actually, like this is my punchline. So does anyone know who Junior Mervin is? Oh, this is I'm a big reggae fan.
Police and thieves in the street.
So Junior Mervin's a guy. But he's a high-pitched reggae singer. So this is a mistake. But you be the judge. I mean, that's the problem with a content-based system. So, but if we had good metadata, like if we collected good tags, we could overwrite those if we had the real tags, if we had the real sort of metadata.
I assume all the songs are not in the list of 500 labeled songs.
These are tenfold cross-validation. So these are all test songs. And actually, when you get the semantic I think for this, I actually just took the semantic multinomials that were produced for each of the test folds and just had a set of 500 songs. I think that's how these ones were calculated. But I'm going to show you a system that works on 12,000 test songs in a second. So does that answer your question? We can talk about it later, too. OK. Anything else? The last part of this is that if we now combine these two words, we get that Jewel song from above. Notice Crosby, Stills, and Nash is gone. We have Jewel. We get this Evanescence song, which sounds a little bit like this.
And it won't leave me alone. These wounds won't seem to heal.
And also, so Crosby, Stills, and Nash is gone. Also, notice this song here by Shakira, which had that rock out sort of electric part, is now also off this list. So, hopefully we're doing something useful. Of course, we make this other mistake here.
Take a message to Mary. But
so the Everly Brothers, again, are definitely not female. But you be the judge of how effeminate their singing is. So that's that. Any other questions? I'm going to get into the quantitative evaluation next, and that might answer some of these questions. OK, so evaluation. So we have this 500-song data set that's been annotated by a minimum of 3 undergraduate Southern California students. And some songs we have as many as 10 annotations for. We're going to take the consensus annotation by combining these 3 or 4 annotations of each song to make, that's what we're going to call our ground truth. And we're going to binarize that, and we're going to say if 75% of the students think this is a good tag for this song, then it's a 1, otherwise it's a 0.
But the tags are not complete. That is, every student puts some random labels which he thinks is relevant.
Well, they listen to the music and they filled out the whole form, and we paid them $10 an hour, and so it is a complete survey from that sense. Okay. So there's no missing data for these 500 songs.
I came in late, but let me just, I think it's a
Sure.
So these 173 words are words that you supplied.
Yeah. Yeah, we gave them a standard form, a web form, and here's all the instrument words, here's all the emotion words, here's all the sort of usage words, and they basically can click boxes or,
Have to select one from each?
Depended on the different kind of semantics. So for emotion, they could pick as many emotions as they want. For instruments, they had to sort of go through each instrument and say, is there none, is it present, is it prominent? So it sort of depends, and we sort of mapped it to be binary, to be real valued weight. But each annotation is binary, 1 or 0, but then when you take multiple annotations from, say, 4 users, you get, 3 out of 4 people said this was a funk song, that kind of thing. So, but for evaluation, unfortunately, we have to sort of come up with a consensus ground truth, which is basically, is this a funk song or is this not a funk song? Binary labels. And we use word precision and recall. So we first annotate each song with 10, so we take our computer audition system, we annotate each song with 10 words, and we basically see how well we did against the ground truth. And precision is just the number of songs that we've correctly annotated with this word versus the number of songs that have been annotated in the ground truth by this word. And recall is just the the number of songs we've correctly annotated with this word divided by the total number of songs that we should have annotated with this word.
So you always do it 10 regardless of what
Yeah, and that's a less satisfying part of the evaluation. But we've done tons of evaluation, and this is just one of the more easy to explain sort of things. And then we're going to average the word recall over all 174 words in our vocabulary. And so if you just randomly label each song with 10 words, you get a precision of 0.14 and a recall of 0.06. Because of the way the numbers work out, some songs have been annotated with 30 words, some songs have been annotated with 15 words, and the empirical upper bound is just found by saying take the ground truth and plug it in. Take the ground truth of 31 words, randomly pick 10 of them to annotate a song, and what's the precision and recall like if you do that? So we're not, usually precision recall is upper bounded by 1, but in this case it's not. That's the only thing that matters.
That precision not be 1? Every word you plug in is correct.
Because some words aren't used that often in our data set, and some words are used very often. So if the word piccolo only appears 5 times in your data set, and
that's recall, not precision, right?
So, because here's what happens. Most songs have been annotated with 35, most consensus annotations. Okay, so here's how it works. If there's, a person will use on the average of about 35 words to annotate a song out of our 174. But when we take the consensus annotation, since there has to be a high level of agreement between users, there might only be 15 words that annotate a song. And then now we're taking 10 words, our system's outputting 10 words. And so when we go from, and then if we take the ground truth and it had 15 words, we're randomly selecting 10 of those 15 words.
I see, and you're averaging it, the macro average.
Yeah. So it's definitely a little bit, again, we've been looking at a lot of evaluation metrics, and there's nothing that sort of is the perfect, metric. But our system outputs does significantly better than random, and it works and the qualitative results sort of show you that it's doing something good. But so I explained that we have let's say we have 4 annotations for a song from humans. We can take 3 of them and create a consensus annotation and see how that 4th person would do against those other 3. And if you do that, you get a precision and recall of 0.3 and 0.15. And what this tells us is not that our system's doing great. It tells us that there's very low inner reviewer agreement for a number of the words. So, the emotions or the usages that people use is very inconsistent. Music's very subjective. But our system's sort of doing a good job of trying to model these semantic words, at least to a level where, we're doing something semantically useful. And of course, if you look at individual words, humans have very high agreement for objective things like instrumentation and genre, whereas humans tend to have very low agreement between emotions and usage. So that's just an interesting sort of thing about music. I mean, that's a very fundamental difference between music and, say, images. So if we look at retrieval, we're basically going to take the KL divergence between each query, and we're going to look at 1, 2, and 3 word queries, and we're basically going to see how well we did. And we're going to use the area under the ROC curve, and most of you might be familiar with this, but we're going to rank order, in this case, 5 songs. We're going to reveal the true labels of these songs. We have 2 romantic songs out of 5. We're just going to trace out the false positive rate versus the true positive rate. And we're going to say we got the first thing we labeled was a romantic song, so we're going to move up here. We're going to trace out as we move down our rank list, we got the second one wrong, so we have a false positive rate of 1/3 now. And as we move down the list, we get our area under we get our ROC curve, and the area under the ROC curve is just integrating that curve. And so that's the metric we use. And then we're going to average the area under the ROC curve for each of the words in our vocabulary. And if you randomly guess, ROC is 0.5 and the upper bound is 1. If you try all the one-word queries in our database, you get, again, something significantly better than random. It's really hard to sort of say anything more about it than that, because there's not a lot of other systems out there that do this, so it's hard to compare. But as we get more and more words in our query, we tend to do significantly better, which is interesting because a lot of the words in our vocabulary are highly correlated. So we're sort of model averaging and doing better. We do. This is over 174 words and 500 songs. So it's I think when we calculated the statistics, it was significantly better between each word. It doesn't. So the number of two-word queries is 174. It's 174 squared, where we have enough. As long as we have enough songs that exhibit these sort of pairs of words. So there's a lot of trials that we can do. There's a lot of queries that we can do. So that's the evaluation. So I'm just going to show you really quickly here. Do we have? So this is the game. I'll show you this at the end. But we have this search engine that I created. It does the standard things like the iTunes store. You can type in the Beatles and do a metadata search, and you can get back. That's going to be a problem. Do you have that number? Yep. Oh, good. Sorry about that. It worked earlier. .cs. I think that was the. Well, if you type Beatles, I'll explain what I was going to explain in this one while John's finding it. But basically, it just does a list of the Beatles songs. This is 12,000 songs now. We've done this sort of semantic annotation, so you can look at them. We also recommend similar songs. Similar songs are just found by taking the two semantic multinomials and calculating the Kale divergence between them for all 12,000 songs in our database. And you can do things like play clips, or you can generate a radio station. Actually, this is a hybrid query, but I'll get there in a second. But that's sort of the user interface. Let's see. Yeah. It's right there. Perfect. Thank you. DT. Oops. Is that a 0, do you think? Yes. AX. 2F. Sorry about that. Hopefully that'll take care of it. Okay, so you could do things, thank you very much. So you can do things like, and you can get all these Beatles songs. And you can play these clips. But that's not very interesting. You can do things like you could do things like let's do something interesting. Well, let's just do aggressive rap here, and again, this is 100% content based, and you get things like Nelly and Eminem. Can you see this, or should I? Yeah. And so you can see, do all these songs by Eminem and. Yeah, well, let's go to the advanced search is kind of the fun part. So this is an example of the vocabulary used. We have genres, instrumentation. So let's do calming and electronica. And let's see what we get. Well, actually, but I think that's a...
Who do you expect that?
Yeah, who do you expect?
Who's in your 12,000? Okay.
Yeah. So, and actually, let's just make a radio station out of it. I like when people have, So I don't know if I don't know actually. I'm not a big electronica fan, so I don't know if these are. But it says Radiohead, I'm a Citizen, Lemon Jelly, Come. Let's get the. I don't know. I mean we can. I can actually show you this. So you can. But I think actually here's something that is a little more useful. You can do things like look for Beatles, and we can play. I'll let you guys come up and play with this if you want. I do totally violate copyright in lots of ways, so I can't give you the website per se because it's our private collection, but I can certainly let you play with it, and I have no problems with that. So if we do Beatles and we say let's pick how about acoustic guitar, maybe mellow here. And maybe emotional. So this is sort of, you can imagine what Beatles songs are: acoustic, mellow, and emotional. Actually, and so you wouldn't necessarily expect the Back in the USSR, but you might expect the Rocky Raccoon, and you get this. Let's see, what's this one? Mother. So this is Mother Nature song, and you can see the semantic, the music Mad Lib that we've output here. And let's hear another one. So these are these are not the Back in the USSR ones. They're not even the Britpop invasion stuff. So, you know. We really can't. Falsetto is a pretty bad one. So, and of course you can do things like generate these playlists. Actually, this is just going to play the search results, but my favorite, Rocky Raccoon. And so these are also the mellow, emotional, acoustic songs. And again, you have to be the judge of whether that matches your search criteria. So, anyway, that's the search engine. What we can play with. It's more fun to play with than to show you in a demo. So, I've used it at parties, and people love to get a kick out of generating playlists and letting them rip. So. Where we're at right now, I'm just going to finish up here. We're trying to legally collect music, which is a very difficult thing. Again, we have this game we want a grant to commercialize it and make it exciting, and that turns out to be very hard. There's these places like Lastfm, which have thousands of tags. Unfortunately, they're all pretty bad. One of the things we've done is used a new formulation of sparse CCA to canonical correlation analysis to find the sort of musically relevant words, and that's an exciting dimension for cleaning the noisy sort of data on the internet. We're doing a lot of web document searches where we collect thousands of websites for songs and artists and musicians, and doing some text mining on a much grander scale. We're doing some user interface design for this sort of music search engines and radio players, and we have this sort of vision of a large-scale system that takes information from the game, trains models, collects information off the internet, and sort of produces this sort of closed-loop music playlist generating, recommendation, gaming sort of environment. There's a lot of great machine learning tests. I know that I've loved reading some of the papers from here because that's what you guys have this sort of philosophy on, doing some music stuff with cutting-edge machine learning stuff, and that's sort of what we're into as well. Like I said, we've done this. We can do acoustic semantic similarity, and we had a paper in ICAST that was about semantic similarity of sound effects. We also entered this data mining contest where we used our system to do similar music, and it was in it finished third, but at the top 4 people were statistically insignificant differences. Modeling correlations between these labels is also something we've been really interested in. There's a lot of models out there, like David Bly's Core LDA model that sort of does a lot of this stuff. There's a paper at NIPS this year about auto-tagging, and it took a discriminative approach that used SVMs. This is by some guys at Sun Microsystems, and I'm in the process of comparing their system with our system, which is sort of a more generative approach. The thing I'm really into in the subject of my thesis is heterogeneous data. We have this game data, which produces semantic tags, but we also have semantic tags from these social networks. We also have web documents and other things like popularity information. How do we take all this data to produce the best sort of hybrid system that uses both social semantic information and acoustic information? The one thing I've learned in all of this research is that music is highly subjective. It really matters on both the individual. You can do some things with demographic information, but even if you were to do a perfect job of modeling an individual, you'd have to model states of an individual because people, as you know, change what they want to listen to on a minute-by-minute basis sometimes. So really focusing on an individual and using that sort of data would be is a very exciting direction. And so that's it. I'll leave you with this great quote that nobody knows where it comes from. It's called. Some people think it's Steve Martin. Others say Thelonious Monk or Elvis Costello. But the truth of the matter is, the more I do this research, the more I realize it's a truism. So talking about music is like dancing about architecture. So maybe all this work is in vain. But that's my talk. If you have any questions, if you want to play with the search engine, if you want to play the game, I'd be happy to show it to you. It's online now. It's exciting. Yeah.
On the previous slide, I'm just curious, you talked about the song similarity contest.
Uh-huh.
Is what happened there that, so this was in general, people were using content-based features to derive.
But
are you saying that you actually extracted semantic labels using the same techniques you presented, and then used those semantic labels to pick music?
Right.
And that competed favorably with other people using purely.
Well, so what we did is we sent them our Gaussian mixture models, and the Gaussian mixture models output this multinomial, and so that's a pure content base. We take their signal and put it through, and there were 12 systems that entered, and the top 4 were sort of all about the same. There's actually a very great community called the Music Information Retrieval community, and there's this data mining contest with dozens of tasks, and it's pretty.
It seems, it's, I guess, pleasantly surprising. I would imagine that most people would take more sort of direct similarity.
Sure.
That like look for spectral
Sure.
similarity between
Yeah.
them. And if you're something that's really semantically driven, competed favorably with that
The winner.
works very well either for your semantic
Yeah.
or says something about the
Yeah.
notion that more direct.
Well,
spectral features.
you're right. All of the top 4 systems use spectral information. A lot of people put a lot of energy into the machine, the signal processing, and we took more of a machine learning approach. And but there's, the other thing is the way the tests work is everybody, there's a couple thousand songs. They pick 60 randomly, and they have humans listen to them and say on a scale from 1 to 10 how similar are these songs, and the average score there is like 5, which tells you there's a long way to go before it gets to sort of human level or commercially viable thing. So when I say we've done well compared to other spectral systems. But the best system will be a system that uses social information, because acoustics alone isn't enough for us to derive notions of similarity.
Yeah, in fact, or some metadata, because I remember in Mongo there was 2 labels, East Coast Gangster and West Coast
I know.
Gangster, and you no way to learn.
But if you play those 2 songs and one's got Tupac and one's got, those kids will say these are not the same. So, it really, the best system is a hybrid system, that uses heterogeneous data to combine notions of similarity and semantics. Yeah.
So since getting these labels of these 174 words or something,
Mm-hmm.
challenge, have you looked at, rather than just correlation between labels, have you looked at the data? I do have labels for the correlation of those labels to data that is available on the web, like reviews,
Yeah.
stuff like that, and then given other reviews,
Yeah.
the distribution of potential labels.
Yeah. So this Lastfm data set, and when you they do have 25,000 unique labels, but if you take labels that have been applied to 5 or more songs, there's something like 2,000 of them. And even if you take those 2,000 and our 174, and we have this sparse CCA approach, where we basically embed semantic information for the songs that we have. We take the 174 words we have plus the 2,000 words labels that Lastfm has, and we just prune them using our sparse CCA approach, and those words generally drop out pretty rapidly, whereas the sort of words we have the survey data for stick around just because the signal is a lot stronger. So the point is that in a tagging situation, people aren't very consistent, or it's very ad hoc, so there's no, how tags are applied. They work well for things like rock and folk, but when you talk about emotions, people don't generally tag with emotions, and they don't tag with a lot of other words, but they tag with, like, I've seen this band live, and there's no acoustic relevance for that ever. So there's a lot of opinionated words that don't have much bearing on the acoustics of the song.
For your precision recall curves, when you take out all the subjective stuff, if you just did a macro average
Over instruments.
Yeah, or like even like what do you know what the precision rate on like vocal is? Like,
We don't do that one. I do. We just have a IEEE journal paper coming out that we break it down by those semantic categories, and I'd have to bring it up. There are people. So one of the things was also there has been a lot of work in this music information retrieval community where someone looks at instruments or emotions or genres, but never has there really been the sort of here's a tag, here's data, let's model it. And I don't know how we would do in a genre bake-off.
Well, genre is hard, but I mean,
yeah,
basic.
An instrument, yeah, where there is a sort of where there really is a ground truth. We haven't done that comparison. I think it'd be worthwhile doing, but you know, so yeah, I mean that would be something worth looking at. And like I said in our journal paper, we do have the statistics for just instruments or just genre or just emotions. And you see that, you know, instruments. What's really interesting is that the inner test subject agreement is so much higher for instruments than as you'd expect. But it tells you that modeling emotion is very hard to do if you're trying to look at a population of users.
And it's kind of swamping your macro average. Right?
Yeah. It is. But we also want a system. Our goal was to design a system where we had a diverse set of tags. We didn't just want to have emotion and we didn't want to like customize each component for each tag. We wanted to say, here are 174 tags, and we're going to treat them generically, and we're going to produce a system that, you know, you could use for thousands of tags without having any marginal sort of difference. So, good. Well, thanks for coming. I appreciate your time.